I'm going this morning to finish the sort of MultiD-MHD that I started yesterday, particularly trying to explain the issue of calculating the electric field. And then in the second part of the lecture, I will address specific questions that I left aside up to that point, in particular the AMR scheme. What sort of complexity does it introduce? How does it work? And then briefly, because I'm a bit short in time, I will address the question of how do you solve gravity in Ramses, and more generally maybe in a grid code, but that will be short, I'm afraid. Okay, so just to briefly remind you what we said yesterday, unlike in the hydro case, where when you go from 1D to 2D to 3D, well, essentially nothing new happened in terms of numerics. It's not the case for MHD because of the difference. I mean, it's deeply rooted in the equation again. You do not have volume conserved quantities, you have a surface conserved quantity, the flux, and associated dV constraint that you have to worry about. As we briefly discussed, dealing with dV is important. If you don't pay attention to maintaining dV sufficiently small, the code will let you know soon, trust me, okay? So we discussed a couple of methods. So this the potential vector method, which is used, for example, in the pencil code, but because you have second order forces, you need to are extremely accurate, so to have very high order methods, which is not the case in most codes. We discussed these Powell methods, which deal with dV by adding a sort of 8-wave, considering an 8-wave problems, but it may have difficulties when you have shocks. If dV is too large, then you may have difficulty with the jump conditions not being accurate. The projection method, which is quite popular those days, so essentially you try to clean the field. So you do your solver, you update the field, it's not dV free, but then you come with recipes to clean this field and to maintain dV low. And then the constraint transport method that is trying to tell you algorithms that dV should be conserved, and then, as I said, it's the ideas of this method is actually to, in a sense, ensure that dV is zero exactly as the mass or the energy is conserved in a typically volume finite method scheme. So that's the same idea. You are removing mass to one cell and you give the exact same amount to another one. That's the same approach with the constraint transport method. You make sure that you will have a 2x2 cancellation of the EMF, which are written there. And this is achieved by doing these sort of circulations where you have an exact compensation of the two IMF here, okay? So that's the mathematical proof, and essentially that's this minus and plus compensation here. So this is quite appealing, but then then the difficulty really is that the electric field is not written in the center of the face. It's written at the sort of the edge of your cell, and this means that you have to do something new to calculate the electric field at this location. Okay, so that's what I'm going to discuss now. So various strategies have been developed. Among the first one that was implemented in Zeus, this mock city, and I guess Jim Stone will be there next week, so he can probably explain this much better than I'm going to do it myself. But so the idea is that they were considering only Alphen waves in this case, and they were trying to do a sort of characteristic methods. So if this is your age, they were sort of tracing back where the information was coming from, using the two characteristics necessary to followed by the Alphen waves. So they are trying to identify where the information comes from and to reconstruct the path followed by those waves. And that's, I think, was efficient, but only incompressible modes were described. Then following, simple method, I would say, some people try to just consider simple averaging. So essentially, you need to know the magnetic field and the velocity at the edge in order to be able to calculate the electric field. So the simple idea, which I think is quite appealing, is to do some simple averaging. So essentially, you will just take the 4 values of the magnetic field around to get the magnetic field where you need it, and the same with the velocity field. And then you can, when you get that, simply calculate the electric field as it should be calculated. The difficulty, so you will preserve div B just because then you apply the city method. The problem is that if you do this, the magnetic field is not, and then the electric field, which is in a sense just a flux, thinking in terms of Riemann solver, it is not properly upwinded, okay? Which means that typically if you have a supersonic motions, all the informations should come from just one direction, the supersonic one, and therefore you should have no information coming from the cells around. So when you do this simple averaging, you do that. I mean, you take informations coming from the region where informations cannot come from, and that's similar to what we discussed during the second lecture when you do the simple averaging or the simple centered method to calculate, for example, the derivatives. The method is intrinsically unstable because you have no proper upwinding. Information comes from region where it cannot come from, and therefore it's unstable. Okay, so because you just do that on the electric field and not on the other variables, it's sort of workish. So people have been working with that, and it's sort of marginally stable. Another approach, which is also working reasonably, I would say, has been developed by Balzara, is to, instead of averaging the magnetic field and the velocity field, you calculate the 4 fluxes at the 4 cells which are around the edge. So the 4 fluxes are obtained by simply solving the 4 1D Riemann problem around, and then so your 4 fluxes give you 4 electric field essentially, and then you just take the average 1/4 of these 4 fluxes. So this is slightly better than the simple field averaging, because when you solve your Riemann problem, you take care of the upwindings, okay, each time at each location. The only difficulty is that yes, you take care of the upwinding, but when you do this 1/4, if you have a situation which is globally supersonic, so if again all the informations come from one directions, the Riemann solver, which is located in subsonic in the downstream, should not be contributing. Once again, all the information should come from one directions or one cell. So it means that in some cases, the upwinding which is performed on all these 4 Riemann problem is not sufficient to ensure that the information is coming from where it should come. Okay, and therefore, I mean, this method is more kind of robust than the direct averaging, but it's not enough for that reasons. Okay, so. I think the right way to really think to this problem has been, I think, more clearly formulated by Landrieu and Delzana in 2000. And the idea is that you shoot terms into a full Riemann problem, a full 2D Riemann problem, okay? Because, so the philosophy of the Riemann problem is that you are working at between two cells, okay, and each of them contributes equally to the flux exchange, okay. So you do a proper upwinding here, but now because you want to calculate the electric field, you are sitting between 4 cells, okay, and formally all cells could have the same contribution, and the upwinding should be really done in a 2D way, okay, taking into account this 4 cell exactly as you would take into account the 2 cells in 1D. Okay, so it's really a 2D Riemann problem, which makes, of course, the problem worse. And then the immediate question is, well, how do you handle 2D Riemann solver, given that it's already a big mess to infer a nice 1D Riemann solver? If you use a linear Riemann solver, and I spent some time describing the class of linear Riemann solver, the so-called rho Riemann solver, so I just give you some hint of how you construct the rho matrix. Well, then it's kind of easy because it's linear. So the idea is that, so this is the 1D flux we were inferring with this method. So I remind you that's the sort of simple or mere averaging of the flux from the left and on the right. And then you have all these terms which will ensure proper upwinding. Okay, this is done on a wave by wave base. Okay, so each, I mean, the signal is propagating at this lambda wave speeds, and that can be seen as a kind of diffusion, if you want. So this can be simply generalized in 2D because it's linear. By essentially taking 1/4 of each fluxes here, so which means 1/4 of the electric field you would infer from these 4 states, and then trying to infer reasonable upwinding terms, okay, and that's where the reasonable can be a bit tricky. So you have to infer what's the rho matrix should be considered. So you have to find a reasonable way to infer your Jacobian. So this A matrix that we were discussing in the last 2 lectures. And so, for example, what you can do is average these 2 states, average these 2 states here, do a Riemann problem in that direction, and then do the contrary. Average these 2, and do a Riemann problem in that direction. Okay. So all these methods will provide reasonable results. Okay. And in practice, that's what is implemented in Ramses at the moment. You know, you have this Riemann parameter that you can pick up from the name list, which tells you how you solve the 1D Riemann problem. And then there is this Riemann 2D parameter that you can also modify or choose in the name list. And typically, when you select Riemann 2D equal rho, this is what is done. We average the state in that direction and so on, and then we calculate 2 sort of Riemann problem, and from that we infer a proper upwinding here that will provide a scheme which turns out to be stable. Okay, so that's okay if you want to use a linearized solver, but as I discussed previously, unfortunately those solvers are not very robust because they are linearized. So when you have to deal with a very nonlinear flow, so typically supersonic turbulence, okay, you have large jumps in many places in the flow, which each time put a lot of stress on the solver, and as I said, it's can often crash. So you have to find switches. So that's a solution which is okayish, but you would like to get rid of this problem. And as I said, one way of doing that is to deal with this HLL type of solver. So the simplest one is the HLL one, as I discussed previously. And here it turns out you can do a kind of nice generalization. So what you can do is actually it has been sort of written by Landru and Delzana, we realize later. But what you can do is say, okay, if I was doing only a 1D Riemann problem, okay, I would have 1 wave propagating toward the left, which is the fast magnetosonic mode, and what toward the right, okay, and the same here, and the same here, and the same here. Now what I can do is that I can essentially replace this sort of 4 or combine this 4 Riemann problem, taking each time the fastest waves. So for example, if I would have waves here and one here that would propagate faster than this one, okay, I can take the maximum of the absolute value between this 2 values, this one here and this one here, and the same for all directions. So I could at the end select 4 wave speed, which correspond to the largest eigenvalue, and that give me this pattern where I have 4 waves propagating away from my 2D Riemann solver. Okay, so I have 4 waves. I have this area. So now I can do exactly as we did in 1D for the HLL, which was just, if you remind, applying conservation relation by integrating first over time and then over space, and then saying that by the virtue of conservation law, the 2 integrations should be equal, and that allows us to infer a star state and then a star flux. You can repeat exactly the same procedure in 2D. So you can, once you get these 4 waves, you can take a volume of controls around and end up with a nice star state. That's one way, I mean, the physical way of saying, understanding the problem. Then there is a more mathematical way, and after you have twisted your mind and done some calculation and so on, you say, oh God, if I have been a clever man, I should have think to that immediately, because you may say, well, if you look at the 1D structure of the HLL solver, you see it's extremely symmetrical. So you may say, okay, I'm going to generalize that in the 2D wave by combining the 4 waves and the 4 flux in a symmetric way, and that's also a nice, more mathematical way to infer the correct flux. Okay, so this is the 2D generalization, the straightforward 2D generalization that you could simply come with by just looking at the symmetry of the HLL problem. So essentially, you combine the 4 flux, okay, in the same spirit that they are combined in the 1D HLL problem. So you weight them by the proper wave speed. Okay, so you have 4 flux combined, weighted by essentially the opposite. So if you are dealing with this flux, you take the 2 opposite wavelengths, okay, and you get up with these weighted sums, and then you pick up also the proper upwinding terms, again based on symmetry, that will guarantee you the stability of the scheme. Okay, so this works. Okay, this leads to a stable scheme. And that works for HLL. Then the question is how you do for maybe more complex solver like HLLD. Well, there are ways essentially to generalize this sort of things. It's become a bit more tricky, but essentially you can do it. So this is the sort of methods which are applied when you select HLLD 2D, well, the HLLD in the Riemann 2D parameters. In Ramses, the electric field is essentially computed using this kind of ideas. And then finally, I'm sure Jim will speak himself about that, so I can probably save my time. So when they in Athena, they find a nice way to compute the flux in the center of the face and to somehow transport this flux at the edge. So it's another idea which has been demonstrated to be very useful and accurate. Okay. Right. So just a sort of a summary. This approach has some advantage. All the electric fields are probably upwinded, so in principle you should be stable, and that seems to be the case. The code is now running extremely well for many problems without crashing. One disadvantage is that in terms of cost, you must not only solve your 4 Riemann 1D problem, but you should, on top of that, solve for the electric field, which means extra cost. And you should also reconstruct to get second order accuracy. You must also reconstruct your field in the edge. And then here I wanted to say some more words on that. The stagger mesh implies some care with this reconstruction. First, for the standard 1D Riemann problem, the By field, okay, must be reconstructed at the center of the face, and as you see, because By is not in the center of the cell, you must do something. Okay, you must transport the magnetic field here. So what is done sometimes is to average these 2 variables in the center, and then we transport them or we reconstruct them at the face. The good news, so that's for this reason that sometimes it is said that the Godunov scheme and the stagger mesh are not, very compatible with each other, which is, true for these variables. But you see, for example, for Bx, Bx is already in place, and it does not need any spatial reconstruction. Okay, so it depends on which variables you are considering. And then finally, you must also, to get second order accuracy, you must also reconstruct the velocity and the magnetic field, not only in the center of the face, but directly at the edge, like this. Okay, which means again extra computation. So that's one of the kind of disadvantage of the method. It introduces more complexity in the code. Okay, I finished more or less what I wanted to say. Oh, sorry.
Why do you need to add the edge or the corner?
Sorry?
Why do you need the velocity at the edge?
It's to calculate the electric field, because the electric field is E dot B, and so when to get the second order, you need to have the field here. Yeah. Okay. So I'm more or less done with this MHD scheme, and now I wanted to say some words on the AMR, and I'm just realizing that I'm late. But fortunately, Tom has already addressed a lot of questions I wanted to address today, so that will save my time. Thanks, Tom. Okay. Right. So, generally speaking, two kind of AMR scheme have been designed. The first one is typically based on this patch. So you have a sort of big shrunk of grids which are added in the flow or in the mesh. So this can be typically 16 by 16 by 16. And the second category are the more tree-based AMR, and Ramses belongs to that category. So the idea is that you have small, oct, just oct, or small grid structures that you will add, and they will be organized exactly as Tom has been describing, using a tree. Okay, so Ramses is belonging to that category, and so it has an oct tree structure. It's a fully threaded tree, which means that all CPU know all the tree. They don't know all the leaf, of course, because otherwise it would be extremely expensive in terms of memory and very inefficient, but they know all the tree stopping at some intermediate level when they do not contain the leaf cells. So each cells will have essentially eight children and the 6 parent cells. So the way the tree is organized is to have 2 linked lists of indices, which allows you to find the parents and the child. And so you have leaf cells, as has been described previously by Tom, and you have inactive cells, which contains the leaf. Right. So the trick or the important aspect with AMR is to find a proper refinement strategy for setting a new grid. So you have rules that you have to follow. First, you, as it is written here, you would like to have some consistency. So typically, you may want to refine to avoid having a big jump in your grid, because that would be a disaster for the physical quantities. So if you typically want to avoid this situation, so having a refinement jump of more than 2, so you will always have to impose that the refinement, that the jump, that the 2 neighbors are at most separated but 1 level, okay? So typically here, that would be, if you have to refine this cell here, okay, you would have to refine this one as well, as it is shown here, in order to have a jump limited to only a factor 2 in resolutions here. Okay, so that's the first rule. The second sort of rules are set up by the physical criteria, and that's where I think IMR is really nice and flexible, is that you are totally free to decide what you want to do, okay? So one criteria of refinement that you have all been using, if you have probably run the test problem I gave you, are this gradient, okay, where essentially you say that you would like the density jump between 2 neighbors be smaller than something like 5% or something like that. So then you say, if my gradient is too large, then I will find it. So that's one type of criteria, which is good, for example, for shocks. But there are many others. The one very nice and very useful criteria is a kind of quasi-Lagrangian evolution. It's essentially saying that you want the mass in your cell being smaller than some threshold. And so if matter piles up in your cells, and if you reach that threshold, essentially you refine it. So it's a kind of, we call it SPH way, because you are really following the mass in a sense. And what is also nice is that you can tune the threshold level by level. Okay, so you can say at the coarse level my threshold is this, and then at the next 2 levels my threshold is that, and so on and so forth. Okay, so you can really tune the refinement depending on the density, for example. Of course, in the context of star formation, the Jeans length is a very important criteria. So you may say, I want to refine my Jeans length. I want to describe my Jeans length, but at least 10 cells, for example. So that's extremely good. You can have geometrical constraints. For example, you may want that only a fraction of your grid is refined. So that depends, that's of course problem dependent, but you may want to have, you see, just the center of the grid. It's very convenient for boundary conditions, for example, which is always a difficult problem. For example, you could have most of your computing cells in the center, okay, where you are really performing the calculation you are instantaneously on. But as we all know, boundary conditions are always a nightmare. So usually the good way to deal with this with the AMR is actually to put them at infinity, and you can do that by having a very, very large and coarse mesh, okay, and then in the regions of interest you put all your numerical power, but you have a sort of smooth a smooth transition, okay, without having to impose something complicated and sometimes a bit arbitrary at the boundary. Okay, so that's typically one of the strengths of the AMR. You can put the problem difficulties extremely far from your calculation domain. And so finally, you may also want to apply this sort of dilatation operator, which means that you may want to propagate your IMR or your refinement further than just the first neighbors. So that would be, say, refining only the grid where your physical criterion has been matched, but you may want to go to propagate the refinement to 1 neighbor, to 2 neighbors, to 3 neighbors. Again, you can decide what you want to do, and that's controlled by the parameter n-expand in the name list. So again, that's a very useful parameter to get good results. Okay. When you want to introduce or to remove a new cell, you have to actually do it. So that's called the prolongation or interpolation operation, and that's controlled by this parameter interpol var and interpol slopes. So you have to decide which value do you introduce here. Okay, so you have to use, for example, conservation laws, but that's not enough. You have also to use a slope, for example. So that's called the interpolation parameter. And when you decide that, or when you see that a cell that was refined previously is not matching anymore at the new time step, the criteria for refinement, okay, it has to be unrefined, otherwise you will end up with a very, very large mesh, and that will be extremely inefficient. So you have to essentially de-refine it. Okay, so this is this restriction operation, and you want typically that if you do interpolation and then the restrictions, well, then you come back to where you start from. Okay, so you have to have these properties of being invariant under this set of operations. Another problem you have to deal with when you have at the interface of coarse grid and refined one, you see, if you calculate the Riemann solver here, you would obtain a flux here, okay, but this flux here has no reasons to be equal to the sum of the two smaller Riemann problem, the two smaller flux that you have obtained by solving this two Riemann 1D problem here. So essentially, you would say, okay, I'm trusting better the sum of these two calculations because they are more refined. So you will not take into account this single flux here. You will have to somehow store these two small fluxes here, and then when you update these cells, the flux you will consider here is the sum of these two fluxes here. Okay, so that's the sort of things you have to deal with also with the AMR. So one of the difficulty is the data structures, and in particular the boundary conditions, which are not, as for example for a grid code, restricted to the actual boundary of your domain. The problem of the boundary conditions is more severe in a sense, because when you have at the transition domain, you can see, well, the way the data are organized and the way the grid is solved is sort of level by level. So starting with the finest level and then doing the minus one level and so on. So at each level, you have the question of this sort of boundary, And the way the calculation is done is that for each oct, okay, you you do the calculation, the hydrodynamical Riemann problem, by essentially selecting a series of oct. So you isolate an oct, okay, and then you pass it to the hydrodynamical solver, which means that each time you are passing an oct, you must pass the proper stencil around to get your boundary conditions right. And the size of the stencil depends on the accuracy of your scheme. If you are first order, then you just need one single layer, so just one neighbor, one ghost zone. If you are second order, like Messel and Koch, then you can quickly see that you need to have two neighbors. So you need to have a layer around your oct made by two neighbors, and that's what is done in Ramses yet. Okay. If you would like to be third order or more, then you would like to increase even more the size of the stencil, and that would become extremely expensive because, as I said, all oct, the way the calculation is organized is by sending octs, which means that if you send an oct, so 2 by 2 by 2 cells, it needs to be surrounded by another layer of 2 cells around, which at the end of the day give you a 6 by 6 by 6 group of cells. So each time you do the calculation, you have to reconstruct this neighbor around your oct, which means that if the cells around are at the same level, that's fine. But if they are not, you have either to smooth these boundaries or to interpolate. Okay, so there's a lot of operation. So if increasing the stencil would be even more expensive, okay, and for these reasons, it's not possible to deal with higher order scheme in Ramses. So you are restricted to second order scheme because of the size of the stencil. Okay, so that's maybe one of the limits of the method. Then coming to the time step issue, I discussed it previously during the first day. So there are different strategies which are controlled by this n subcycle parameters. You can either synchronize all your level and do just simple or unique time steps, but you can also subcycle, so which means doing 2 time steps when you do at the finest level. Okay, so you have to each time modify the buffer around, and you have to record here the fluxes to store it in such a way that you will use it when it will be needed here to update the cursor level. Okay, so you have to store this intermediate flux in order to use it when you will reach the course level update. Okay, so that's also something you have to worry about when you deal with an MAR scheme. One of the limits or one of the difficulty that AMR is facing is that if you are second order, you can quickly see that when you have a jump in your resolution like this, you are losing your second order accuracy. Okay, and that can be inferred by doing this Taylor expansion. So when you do the Taylor expansion, so you have this sort of alpha parameters that sort of describe the change of resolution. So if alpha is equal to 1, then you recover the 1 as it is here, but otherwise you modify this coefficient, and then as you quickly see that if you would like to be for a first order scheme, you would like, if the only way to get rid of the first order terms here is to have an alpha here, which is not what we have when we are dealing with the advection equation. So it means that there is a first order terms around, and for the second order scheme, as you see here, you do not cancel out the second derivative, which means that you are losing one orders in the scheme. Okay, so that's unavoidable, and it means that when you are at the location of an AMR scheme, you are lost the second order scheme, and even worse, you see that this number here, because alpha is typically larger than 1, is going to be negative, and as you see, it's second order terms, which means that you generate something like a negative viscosity. So that's a bit scary. So that means that you may have instabilities here, well, fortunately, this is located at only a few points, but you see, for example, this kind of feature here maybe a sign of this. So I'm at 5 minutes. Is that?
These are 10.
Okay, good. So yeah, just maybe to stress a bit more, after having stressing the difficulty, the advantage that you can get from this AMR scheme, it's pretty obvious from this simple shock tube test that's performed on a regular grid. So you see all the discontinuities are not extremely well described. There is a sort of slight overshoot that you often have in shocks, and you see this contact discontinuity, which is already difficult to catch, is not extremely well described. And so the only way to do better would be to increase the resolution. But then you see you spent most of your time with a regular grid to describe nothing, okay? Because this discontinuity typically located at very special position of your flow, and most of the flow is totally smooth. So if with an AMR scheme, of course, you can put your cells where it is needed, and nothing around. So you see the mesh points here are very coarse here and very refined here. So by then you can get something extremely smooth and extremely accurate, close to the analytical curves. Okay, and I will encourage you to typically do this exercise. So run third test, for example, using a uniform mesh with low resolution, because then you can really see the problem. And then you try to push your resolution without using AMR to try to improve the agreement between the numerics and the analytics. And you see you can do it, but at the expense of doing very large calculations. And then you switch the AMR, choosing properly the refinement parameters, and you will see the calculation being extremely fast, and the quality of the calculation being extremely good. So that's where the AMR is really strong. So typically there is this debate when you so in the example I just showed you, it was easy because the AMR, the discontinuity were located at only a few positions. If you have a more complex flow, it depends on how complex it is and what fraction of the grid should actually be refined. So that is totally dependent on the problem, and I'm not sure there is a general rule that can be inferred. For example, here, that's probably a marginal case. You see, you have to refine a significant fraction of the grid. You may win a little bit here and here, but the grid is heavily refined. And of course, there is some overhead due to the AMR. So that's always a compromise. So this is problem dependent, whether you should use it or not, and how you should refine it. I think I already showed that during the first day, so I can probably skip. So yeah, just to summarize a bit, so the Ramses is based on this tree-based AMR octos tree structure. So each oct is knowing the list of its neighbors and child. There is, in order to deal properly with the AMR on overhead, which can be up to well, something like 50% or more. So if your problem is, I mean, if the AMR gain that you could have is not so large, then it may be worth doing the problem with the Cartesian grid. So okay, it depends on what you want to do. And then so you have this various models. So the n-body module to do gravity. So this particle mesh method, which allows you to reproject the particle onto the mesh to get to do the gravity. So the hydro modules and this time integration. Of course, other modules are implemented in Ramses. So we now have cooling, radiative transfer. Some chemistry now is already available and will be developed further soon. So finally, I wanted to discuss a little bit more this domain decomposition issue, but Thomas has been doing it already. So yeah, this difficulty, or the difficulty is how you balance, how you perform this load balance, how you attribute to each CPU the calculation you must perform. And maybe there is another layer of complexity with the AMR, is because at least the way Ramses is organized is because the calculation is done level by level, starting at the finest level and then going down through level. So one of the problems we are facing at the moment is that the load balancing strategy is exactly identical to what Thomas described. So I'm going to present a few of them, but essentially it's a global approach, while the calculation is done level by level. Okay, so that's one of the difficulties. You may have something which is well balanced in terms of computing cells, but if you have many levels in your calculation, and if none of this level is dominant in terms of number of cells, it means that also your calculation could be globally well balanced. Level by level, it may not be well balanced. Okay, just because it may end up that one CPU is carrying most of the cell at a given level, say the maximum level, another CPU is carrying no cell of that level. Okay, which means that while your CPU A is doing is having a hard job, the one CPU B is doing nothing essentially. So that's kind of problem I think generic to AMR codes, and I'm not aware of any good solution at the moment. Okay, so so maybe I should skip this because I'm running out of time. So just quickly saying, so you have various load balancing strategy, and there are again the best strategy may be problem dependent. For example, in this sort of set of tests, the angular strategy is probably the best. So you refined the load balancing is ensured by doing sort of angular decomposition. So it's really problem dependent. I mean, it depends of what you are doing exactly. and I wanted to say a little bit some words on gravity on a grid. So you essentially have to discretize the Poisson equations, so which is a second order equation. So in 1D, the problem you have to solve is essentially this one. So this means that you have to essentially invert this matrix here, okay, to find the potential. And so the problem can be seen as a Fourier transform. So as a matrix inversion. So if you were doing Fourier analysis or Fourier transformation, that would be extremely easy. The problem is that, again, because of the structure, the complex structure of the mesh, which is very irregular, you cannot easily perform a Fourier transform. So you have to use another method. So typically at the moment, two methods have been developed and are available. The first one is the so-called relaxation method, the SOD method, where you do some sort of iteration and trying to get a kind of relaxation. And the second one is the conjugate gradient. So I'm going to spend the rest of my time to describe it briefly because it can be used for other type of equation. So the idea is that the matrix that you should invert turns out to be symmetric, and that's an important constraint. The matrix must be symmetric. So in that case, we know from the mathematician that there is a basis of normal eigenvectors, which means that there are vectors which have these properties. So their product is 0, and that would be the key. So if you write x and this basis, and you apply your matrix to this vector, and if you multiply then by one of the vector from this basis, then you find that this product here is equal to the component multiplied by the product of P by itself through A, and that's give you then the component of the coordinates of x on this basis. Okay, so in principle, if you can find this vector, then you can immediately obtain or invert your matrix. Okay, the problem is that the matrix is very large. Okay, so it's in the context of our context extremely difficult to actually write down this matrix and to find all this vector. So that's not a good strategy. But the idea is that maybe we don't need to get a good approximation to know all these vectors and all these coordinates. Maybe we need only to know a few of them. Okay, so that's the idea. The idea of the algorithms is to find an iterative procedure which will allow us to identify the important vector and to go recursively through all of them up to the point where some accuracy threshold, okay, will be reached. So that's done as follows. So we try to minimize the quantity which is written here, okay, which is exactly the system we want to invert. So if this is 0, then that's it. We have an exact solution. So and the gradient of this quantity is precisely what we are trying to solve. So the idea is that we start with a guess x naught. We can then calculate the residual, which is the difference between what we a times the guess minus b. And more generally, if we reach a certain after a few steps, a certain guess or a certain approximation, we can define a residual which is given by this. So the idea is to not, I mean, more or less is to try to infer the next direction along which the minimization should be performed. And the obvious guess you can have is to use the gradient. The problem is that if we were using only the gradient, there is, I mean, the two consecutive gradients would not be orthogonal, so and they may be sometimes almost parallel. So the minimization for that reason would be extremely inefficient because we'd be going more or less along the same direction. So the idea of these algorithms is not to use the gradient, but to correct this gradient by a terms, which turns out to be this one, which will guarantee that all the arrays along which the minimization is performed are all orthogonal to each other. Okay, and by doing that, you sort of maximize the efficiency of your minimization. So that's really the spirit of this method, and this is again rooted in the properties of the matrix, which admits an eigenvector or eigenvector which are all orthogonal to each other. So once you have calculated this new direction along which the minimization should be performed, you have to infer the optimal, I mean the best coefficients that will make your approximation as small as possible. And then again, mathematicians tell us that the optimal choice turns out to be this one. Okay. So this, in practice, the method is quite useful. It's not difficult to implement, and in particular, you do not have to store the matrix. Okay, so it means that you do not need a huge memory to do this. And there are many situations for which you need to solve this kind of equation. If you want to do, for example, implicit resolution, for example, for the heat transfer or for the radiation transfer, you will need to invert a similar type of matrix. And for example, the relative transfer module, which has been developed recently in Ramses by Benoît Commerson, is solving implicitly the terms in the relative transfer equations, which are also second order method following this second order scheme following this method here. Okay, I think I'm done from what I wanted to say. So thank you for your attention.